Now, conveniently, Mark already introduced the biggest subtlety involved here, which is really important, which is that actually this is an integrated level expression. Why is it integrated level expression? Because the scalar boxes are not a complete basis of one loop integrands in 4 dimensions. This is only valid up to terms that integrate to 0. And so we're not going to match in field theory at the level of the integrand in terms of these scalar boxes. The reason is basically because they're scalar. Okay? Now, Mark alluded to this in that when you the solution to these 4 propagators going on a shell, there are always 2 solutions to this. So there are 2 residues, and the global residue theorem tells you that the residues of the 2 are equal and opposite. And so this thing has to have, whatever they are, you can normalize it to 1 if you'd like, but the point is that they have to add up to 0. And so you know that this thing has equal and opposite residues. But in field theory, this corresponds to evaluating these 4 trees on different values of this L star. So L is either the first one, which I'll call quad cut 1, or it's quad cut 2. And the point is that this is not this has some extra index I, and generally F1 is not equal to F2. The reason is because these are parity conjugates of each other. That's what this means. This conjugate is a parity conjugate. And the product of these amplitudes and the parity conjugate clearly is not usually the same unless it's a parity invariant amplitude, which is maximally broken, for example, for MHV, where in one case, on one of the cuts, so on one of the solutions to all propagators going on shell, you get the tree amplitude, and the other solution you get 0 in field theory. Okay, but that doesn't really bother so much after integration because this is just parity. And so the parity symmetrized integral you can match by just summing the 2 solutions. And just to make that really abundantly clear, I'm going to say it's F1 plus F2. And this is the usual expression. Now I want to make it clear, of course, this looks extremely prescriptive. This is a closed formula for the integrated expressions. At 2 loops, this becomes very difficult, partly because the choice of integrals involved, there's a lot more choice. The normalizations it opens a huge realm of possibilities, and the coefficients are much, much uglier, and there's linear algebra involved for sure in the usual approach. So the first step I'd like to do is to actually get this to an integrand level expression, and to try to construct this so that we're matching singularities one at a time prescriptively. And the way to do that is actually, well, it's not that complicated. The idea is to take each one of these solutions and to just basically think about what we know from field theory. We know that there are these points. N choose 4 points times 2 in field theory space that we know exactly what field theory should give. So there's N choose 4 times 2 special places where we know exactly what field theory gives, and we want to take each one of those special points in loop momentum space and decorate it by an integrand that matches that residue exactly and none others. Okay? Now there's actually a little bit of a problem. So the idea is we want to somehow chiralize this thing so that it matches one of the solutions and not the others, not the other. And the way to do this, now what I'm about to describe is a complication that only happens at one loop, and it's a little bit, but it's clear why. So there's no way to take a 4-dimensional integral by the global residue theorem. In order to have this residue, you need to have at least 4 propagators. And if you have 4, the global residue theorem tells you that the residues are equal and opposite. So you don't learn. So there's no way to hit it with a box integral. And you could go to a pentagon. And what I'm about to suggest is going to dirty the answer a little bit, but it's really a good idea, which is to introduce a fake extra propagator. Why? Because you introduce a real extra propagator, a real pentagon, it has lots of physical cuts. And you don't want to match, that requires linear algebra to fix. And so instead, introduce a fake extra propagator so that this thing gets chiralized into an integral into, call it I. I'll give the example for 1, which is the scalar integral times one extra propagator, which I'll write, I'm not going to have much notation here, but I'll say an arbitrary extra propagator like this, and then some numerator that depends on L, that is engineered exactly so that on this cut, on the cut Q1, this as unit residue and is 0 on the other residue. That's enough conditions to uniquely fix this. So this uniquely fixes these chiralized integrals. And by decorating each one of these leading singularities by the appropriate chiralized integral, you are guaranteed to match every single one of these plot cuts exactly once. And so now what we have is we have this, these nice chiralized integrals. We can remove the parentheses. I2, A, B, C, D. So these things depend on Px, which is, of course is spurious. But we know that the physical cuts of each integral exactly match that leading singularity and that leading singularity alone. And this whole expression is guaranteed to match field theory on every leading singularity of this type. Okay, two caveats, two points. First, we need to check that it doesn't depend on x, right? That's important because every term in this thing depends on the spurious extra propagator. And we need to make sure the final expression doesn't have it. It's important. But the other problem is actually related to the question I asked Mark after his talk, which is a subtlety that's very rarely noticed here, which is that we've actually lost part of the answer. We are no longer matching field theory on every single codimension 4 residue. And the reason is because not every codimension 4, not every leading singularity looks like a box in n equals 4, the long jet. And the sharpest way of seeing that has to be the case is that every one of these chiral integrals, as soon as you add this extra propagator and you add this numerator appropriately normalized, is guaranteed to be finite. And so this whole thing is finite, term by term. And so clearly we're getting the wrong answer. What happened to all of our infrared divergences? This every term. So we have now a finite expression which matches field theory on every box, okay? But it's finite, we're clearly missing something. And the resolution of this little problem is the fact that we neglected not every single codimension 4 residue looks like a box. There's another kind which is directly associated with soft and collinear divergences. Divergences should ring a bell. We're missing divergent parts, okay, which correspond to cutting 3 propagators. And they have this topology. So first, if you just imagine taking in field theory and cutting these 3 propagators, which you can clearly do between any A plus 1. Okay? This is a codimension 3 residue. But on the support of this, so what does this look like? Again, I'm not going to have much notation, but this is going to be like L minus PA squared, L squared, and L plus P A plus 1 squared. It's this. Talking about. And if you take the codimension 3 residue, actually you don't even need to take the whole codimension 2. On the support of any propagator going on shell, the adjacent propagator is factorized. So on the support of this equals 0 and this equals 0, L squared becomes the product of 2 factors. It's just the angle bracket, square bracket. It's very easy. And you can actually cut it twice. And that corresponds to sending the momentum to first putting everything on shell and then sending this momentum to be 0. This is a soft collinear divergence. And these codimension 4 residues, so I'm going to cut this one twice. This is what's historically been called a composite leading singularity, but who cares about composite? The point is it's leading. It's a codimension 4 residue, and it's something that we know exactly what field theory has to be on this point. So there are n extra points in loop momentum space where there are extra residues, and the residues are trivial. They're tree amplitudes. Why? Because setting this momentum to 0 results in this graph, which is just a tree amplitude. Okay, so there are actually n choose 4 times 2 points that correspond to boxes, and there are n points that correspond to these little kind of double cut triangles. And when we chiralized all the boxes, we actually lost their ability to hit these leading singularities. And so to make that up, all we need to do is, again, decorate this by an integral which is guaranteed to match that cut. And that cut, the value in field theory on this cut is exactly just the tree amplitude. And we just need to decorate it with an integral. We're going to add an extra L plus Px, this extra thing, and a numerator that depends on Px in this case, it's independent of L. But the point is that the numerator is chosen exactly so this is unit residue on, unit valued on this cut. Okay, we introduced that. And this will define to be, let's see, maybe I should call it T sub A, and I'll take the sum of TA, which each one of these things are individually divergent, and call it I divergent. Or maybe I can just call it T, but okay. So this thing, so there's an extra term that we're missing, and to match the rest of the cuts, we have to add a tree times this sum of triangles. Divergent. Okay, now the right-hand side matches every single codimension fourth residue of leading singularity, and it's not a hard exercise to show that it can be shown by a global residue theorem that it's independent of X. It gives the right answer, and so we're done. This is only one extra term relative to the ordinary box expansion, and this correctly reproduces the output of, say, BCFW at one loop. So it fully matches the field theory at the level of the integrand. And it's not yet clear how to generalize this to include the bubbles and triangles, but that will become clear when we see what the result looks like at two loop.
Does the OPP representation do this too?
The OPP representation,
they put in a spurious Fox term that has a leverage beta with a loop momentum.
it absolutely
It
should.
doesn't have any PX dependence in it at all.
So if you included, say, pentagons,
It doesn't have pentagons.
well, then it's not going to match the integrand. Right, with that
It
pentagon,
has a box that's linear in the loop momentum.
a box with linear.
And that splits the two solutions.
No, the global residue theorem tells you that if you have exactly four propagators, the residues will be the same. Right? Right, it's all the solutions to the four propagators.
It has loop momentum in the numerators of the boxes.
It doesn't matter. The sum of all residues is 0. Right.
I think it works. Okay.
Okay. So, but anyway, I'm pretty sure you can't get away with just boxes. But anyway, I don't know exactly how it compares to that. But this is valid at the level of the integrand. And although this was derived as tweaking the usual story of one loop, I want to emphasize that this is very prescriptive. The idea is very straightforward. You take a given leading singularity and you decorate it by an integral which matches that cut and none others. So you don't want to have any other physical cuts in it. And as soon as you do that, you break it up into every single cut that you know about in field theory. You get these box-like ones and you get these triangle-like ones. And it has this kind of accidental and remarkable feature, which is that it breaks the answer up into one loop finite plus one loop divergent. And the divergent is manifestly proportional to the tree amplitude. That has an amazing accidental consequence, which is that in this, as soon as their amplitude is represented in this way, the ratio of any two amplitudes is manifestly finite term by term. And so this gives you a representation of L loop integrands, which has the property that the ratio function is always manifestly finite term by term. The only thing you could possibly complain about is that this X dependence term by term, and I don't really know how to fix this at one loop, unless this OPP solution works. But this is not going to be necessary at two loops. At two loops, we will not need to introduce extra propagators to match every cut one at a time. Okay, before I move on to two loops, do I have any questions about this one loop story? Yeah.
Does that one loop finite function you introduce as any large logs for the external momentum when we have large ratio?
Sorry, large logs.
So if the external momentum has some large ratio,
Yeah.
does that finite function include those large logs, or they're all in the divergent triangle function?
I'm not sure. And every term here is just everything here is analytically known. It's just a bunch of dialogues and log logs. Yeah. This one has some finite parts in it, which is a little unfortunate, but otherwise it's just manifestly log squared divergent. So, okay.
By analytically known, do you have to specify what your PX is? Or is it
It's a function of X. So term by term, you get a bunch of things that involve cross ratios depending on X. They would be dual conformal invariant except for the fact that it depends on X. This X dependence is not actually going to be necessary. Okay. Now, although I started with the boxes because everybody knows and is familiar with the boxes at one loop, it's actually conceptually, it's actually much cleaner to go in the other direction. You see, because the more singular one, the composite leading singularity, this triangle one, was actually the easiest to fix, because it was just the tree amplitude times a bunch of ordinary simple integrals designed to exactly match that. And in fact, this continues to be the case. And it turns out to be a much more constructive and straightforward procedure. To start with the most composite, the leading singularities you know that involve the fewest cuts or fewest propagators, match those, and then successively add more propagators, matching more cuts as you go. This is a very constructive, very efficient procedure that I think should continue. Just find it 3 loops and higher. So let's do 2 loops. Okay, so the expression we're going to get is going to be very similar. We're going to have a cut, an on-shell diagram, and we're going to decorate each one that we know about in field theory with exactly an integrand designed to match that cut. And so let's start with the most singular possible terms, which are these like triangle ones, these composites, these soft collinear divergences, but soft collinear in both loop momentum. So this is that kind of divergence squared, and it corresponds to an on-shell diagram, a codimension 8 residue, where you cut there are arbitrary lengths between. The point is you cut some like there, and you cut these things, and you cut the middle ones twice. Okay. So this is a codimension 8 residue involving only 6 propagators. And you know that this is associated with the most singular part in the amplitude, the most infrared divergent part of the amplitude. And you decorate this thing by an integral engineered to exactly match that cut and none others. So, well, not none others, sorry, but engineered to match that cut. That's actually an important caveat, because it's going to match others. Okay, so you multiply this by a scalar integral involving these 6 propagators, also this L1, L2, and this integral, of course, you have to normalize it, and the normalization of this integral, so you take these 7 propagators, and you normalize it unique by the condition that it has unit residue on that cut. Okay, so this is a completely specified integral. Doesn't matter what notation or whatever you use, it's just normalized to have unit on that cut, and now we've guaranteed to match field theory on every one of those cuts. Okay, now that's actually it for soft times soft, soft collinear in both loop momenta. But now we have to talk about the ones where it's just soft collinear in one of the loop momenta, and they have 2 different kinds of topology.
When you say normalized to match field theory, you mean if you multiply by H3?
That's what this thing is equal to. This on-shell diagram means H3.
Okay.
Yeah. So there's another kind which, another on-shell diagram we can draw that involves cutting 7 propagators. Or this one involves cutting 6 propagators. There's an on-shell diagram that involves cutting 7 propagators. That's associated with one of these divergences. Oh, and actually, I know this is perfect. Yeah. Okay. And it has some other indicators. Okay. So we know what this is in field theory. So it involves cutting this one twice and every other one you see. This is just a simple function. It's not as simple as the tree. But notice that it's basically a box. This is exactly one of those Fs. This is a 1-loop leading singularity. Okay. And we know that there should be this kind of a cut, this maximum this leading singularity in field theory. So we want to multiply this by a scalar integral exactly engineered to be unit on that cut. Now, to be extremely pedantic, there are actually 2 cuts in this topology because there are 2 Fs, of course, and so you should multiply and this thing has you normalize each one separately. Turns out it doesn't make any difference in this case, but anyway, that's the point. So you take the 1-loop leading singularity times this integral normalized so that it matches it on exactly that cut individually. Now, the last one that involves 7 propagators is not that different. It also looks like it is, the leading singularity part is a 1-loop leading singularity as well.
Jake, can I ask one question?
Yep.
So how do you distinguish the chiral solutions for this 2-loop guy now? Like you only have a box integral, so you can't write a non-trivial.
You're going to sum over them, so it actually doesn't matter, right? Yeah, sorry, yeah.
So now you take the.
It's for each one separately. Yeah. Sorry, I mean it doesn't make any difference. Let me define this to be the sum of the two, and then normalize this so that it's 1. Okay.
What do you mean by cutting twice?
So it means it's from this. So on the support of what? On the residue where you set this thing equal to 0, L squared factorizes. So you're going to set, so this thing becomes, in spinor Helicity notation it's easy to write, but it factorizes. And so you can set each factor 0 separately.
Sorry, Jake, if I just look at the 3 cuts where you have a double cut, shouldn't I just,
Which one? This one?
the middle diagram?
The middle diagram.
Yeah, and just cut the triple cut with the double cut that makes it a soft, yeah.
Yeah.
So shouldn't I just directly see the 1 loop integral and it's full?
No, you want to have 2 loop integrand that has this cut. So the residue
Yeah,
is
the residue is just a full 1 loop integral.
not the 1 loop integrand. This is individual diagram by individual diagram. There are lots of diagrams in this topology, right?
Okay.
Depending on how the legs are distributed and stuff like that. And each one you decorate with a box designed to match that one. Okay. You can think about it in the other direction and say, take all the 1 loop boxes like this you have, and add this thing to all possible
Yeah,
edges.
that's the
Yeah. Okay.
I have a
Oh, but you might be looking ahead of me, which is an important point. So hold on to that thought. Okay. So the last one is like this, where you just basically attach the soft collinear to one of these corners. In which case, it's also clearly just the field theory residue is just the 1 loop box, and you decorate it by again an integral designed to match that cut and none others, which is a pentabox, a divergent pentabox, like this. Okay. Now in this case, you're going to sum over both of them. There's nothing really chiral here. In this case, there actually are kind of 2 of them because this pentabox is a numerator, and it's different for the different cuts. So again, this you're going to decorate the ith box of this topology by a pentabox designed to match exactly that cut and just that cut, and uniquely normalizes it. So we've got 3 terms in our expression so far. Completely constructed. We just started writing stuff down. And one thing that's interesting is that unlike the case of 1 loop, these integrals do have other cuts, and they contribute to other, this is not I'm not writing an exhaustive list of cuts at 2 loops, I'm just writing a minimal list of cuts. So I'm just writing enough cuts so that everything else gets matched by residue theorems. But this might have been what you were referring to earlier, and this is a truly remarkable kind of accident. This thing is clearly, well, let me erase this. I don't need a header. This might have been what you were alluding to. But this term is fairly manifestly a tree times this 1 loop divergence squared. And this turns out to be, and this actually requires a little bit of work, but it turns out, but it can be shown in about a page of algebra, that this happens to be the same as a 1 loop finite, fully at the whole integrand level, by the way. I mean, the entire integrand is the 1 loop finite integrand times the 1 loop divergence, which is a tree times this divergent. Okay. So it's exactly 1 loop finite times 1 loop divergent. Oh yeah, well, so far we haven't matched the full 2 loop amplitude, but this actually captures all the divergent parts of it. And so even if I just stopped here and the whole story were done, and I just said it's this plus something I'm going to call finite, I'm just going to define it to be finite. It's a relatively straightforward exercise to show that as soon as we've captured the divergence in this form, so that it's 1 loop tree times 1 loop divergent squared and 1 loop finite times 1 loop divergent like this, that the ratio of any 2 amplitudes is manifestly finite term by term. Because what's happening here is that the divergent part of the amplitude is exponentiating nicely. Still remains to be shown exactly how to capture this finite part that remains, but the divergent parts, which we've just captured completely, are arranged so that the ratios of all amplitudes that the divergences of the ratios of amplitudes cancel directly. Okay. So, in the time that remains, last bit, I'm going to talk about this two-loop, the finite part. So we need to talk about some more cuts. And the first thing, on this over here. The first thing, to continue the story, and this actually took us an embarrassingly long time to really realize, and it's related to this to something nice that happened in one loop that doesn't happen in two loops, even in planar n equals 4, is the fact that this story of just fixing all these codimension 8 points, we know what field theory looks like at this codimension 8 point, this codimension 8 point. We know what it is at all these points. But even knowing every single codimension 8 residue does not uniquely fix the two-loop amplitude. And the easiest way of seeing that, the most concrete way, I think, is just to look at a particular component. Consider, for example, the all-scalar amplitude, the 10-point amplitude, where you have phi 1, phi 2, phi 6, phi 7, to phi 10. Okay, so it involves 10 scalars. This is just a component amplitude of the full n equals 4 amplitude. And it's the one where particle 1 has R charge 1, 2, and particle 2 through 4 has R charge 2, 3, and particle 6 has R charge 3, 4, and 7 through 10 have R charge 4, 1. Okay, so this is just some eta component, some particular component helicity amplitude in the full 10-point n cubed MHB amplitude. Okay, but it's just some component. You can compute it any way you'd like, including with BCFW, and you find that this whole thing, this entire amplitude, is equal to a single Feynman diagram. It's equal to 1, 2, 3. And there's no numerator here, because this is a scalar. This is exactly something in phi 4 theory. And it is literally that phi 4 Feynman diagram. That is the entire 10-point n cubed MHB amplitude on this component. It's just a single Feynman diagram. And as we saw yesterday, this thing, because it's massive at every corner and it's massive on the interior because of these extra legs, this thing has codimension 7 residues, but it does not have a codimension 8 residue, because on this codimension 7 cut, you get an elliptic curve, and this elliptic curve has no further singular points. And so clearly we can't fix the full answer by fixing it on all codimension 8 points, because there are component amplitudes that don't even have codimension 8 points. It's like n equals 4 is requiring that we include triangles like at one loop, right? It's things that are not maximal leading, not leading singularities. We need to somehow fix these lower cuts separately. Okay, and I'm embarrassed by how long it took us to figure out the right answer, but in retrospect, it's pretty straightforward. The idea is, who cares? The codimension 8 residues are the weakest constraints. Much stronger is to fix all codimension 7 residues in field theory. Even stronger than that is to fix codimension 6 residues. And so actually you can fix a lower cut to field theory and guarantee that you're going to match field theory. It's the lower the cut that you match, the stronger you match everything lower for free. So the idea is that we don't know, there isn't any special point, any L star, any isolated point in loop momentum space to match that kind of a cut. And so, but we know what field theory looks like on a cut like this. So let's consider this codimension 6 residue in field theory. Okay, now this, as a leading singularity, as an on-shell diagram, depends on 2 additional degrees of freedom. And the easiest, if you're familiar with on-shell diagram kind of technology, it's kind of obvious, but there are a lot of ways of thinking about it. One way is to think about it as a codimension 6 residue of some 2-loop object. But you can also think about it by multiplying all the delta functions and the vertices and integrating over the phase space of the internal line. But the point is that this is an on-shell function, is something you can compute using however you'd like in terms of R invariance or whatever. But it depends on 2 internal degrees of freedom. Right? So this is, whatever this thing is, it's some function of x and y. It doesn't matter. It's a function of 2 variables. And we know that in the xy space, there's no special points. There's no codimension 2 points. Because that would correspond to a codimension 8 residue. So there's no preferred points in the xy plane to fix this to the right answer. The good thing is that we don't need to. It doesn't make any difference.